Hi, so tonight I am going to be describing and with some video showing you how to take a three-phase motor to pieces that is wound for permanent high voltage, split the wiring inside and make it a dual voltage three-phase motor. You're obviously looking at some wavy lines here. This is what wiring diagrams look like to most people, so hopefully my following pictures and video will make it a little bit easier for people to understand, and maybe you can have a go at modifying your own three-phase motor to be able to run it in your home workshops. So as a garage mechanic, we get shown pictures like this when we're learning about alternators and how alternators work in automotive processes. On the left you're looking at the delta, and that's a low voltage, and on the right you're looking at a star. The star's the high voltage, if I didn't mention that already. What you're looking at, where the wires come out, if you measured resistance at the place where the wires come out, you'll notice on the delta you're only measuring one coil, whereas on the star you're always measuring two coils. Now if we refer to Watt's law, which we have to do as a garage mechanic, Watt's law states that the power is the sum of amps times voltage. So if you've got more amps going through a circuit, you need less voltage to get the same power, vice versa. Here I've made it a bit clearer for you to see what's happening. The red circles at the bottom is where the wires would be coming out, and you'd be linking your wires in from the wall into that area. So if you took any two of those wires and measured resistance, you'd clearly be going through one coil, through a little bit of a wire, and then down through another coil and out into your meter. And that's why you get to measure two coils in star, and you can use high voltage and still get the same power. Whereas in the delta, the low voltage configuration, this is what the schematic looks like. It's a bit strange, but if you break it down simply and take any two of those dots at the bottom like we did before and follow the lines, you will notice that you will only ever be measuring one coil at a time. So let's take the far left one and the far right one, where we've got the black joining wire going from one coil to the other. It looks really confusing, but if you just look at the two red dots at the bottom, you'll notice the one on the right side is at the bottom of that right coil, and the red dot on the left side is just going straight up to the top of that coil. So if you put your test meter across those two, you're just measuring that one coil. Now let's take the far right one again, and then let's take the center one. And now you look, it's touching the bottom of the center coil, and the wire, the linking wire, is going to the top of that coil. So you'll just be measuring that one coil, hence the resistance is lower. So this picture gets even more complicated, and I don't think I really want to fully explain what's going on in this picture. You can just pause it and see that this is delta configuration. And this is the low voltage configuration that I want to change my Bridgeport motor to, so I can run it at 220 volt off an inverter. On the right hand side you see the box. Hopefully that represents what you would see on a three-phase motor. When you open up the link box and you want to put your wires in, you'll see 6, or sometimes you'll see 8 ports, but you only need the 6 ports. And inside the motor you've got your three-phase coils, and they will be linked to that box in this kind of configuration. And then inside that box you've got the violet coloured bars going around the screws, and that's the way we link it in delta. just changing the picture here quickly to show you this is how it would be linked in Star. Going back to the Delta picture, this is the ideal where I want to get the motor wired up, and the ideal is to get all the coils A, B and C wired in series. So if we notice, coil A, port 1 is going all the way across onto the box where it says A. A1 if you look at the box, and then A2 comes down to the bottom of the box and goes into A2. So A2 goes into B1 and B2 goes into C1 and C2 goes back into A1, and that forms the whole loop. And it's a continuous loop all the way around the circuit. Here we're looking back at the Star configuration, and the 3 wires would be going in on the 2 port here from your wall outlet. But I'm not concerned about this because I'm not going to be using this. I'm taking my motor out of this configuration and putting it into Delta, so I don't want to spend too much time looking at the way this is wired, to be fair. So on to the video, and here I am first stripping the Bridgeport's feed motor, and you'll see I'll make a few mistakes. Not critical because I've got 3 of these motors, but later on you'll see me stripping the Bridgeport's main drive motor, and this goes successfully, fingers crossed. Not quite finished yet. This is part 1 video, part 2 video following when I get all the insulation. Three-phase motor. On the casing it says 1/8 horsepower, 220 to 250, 380 to 440 volts. But it only has 3 wires coming out of it, which means it is wired one way only. So I'll give it best for the evening,
but I have figured it out. So we've got the 1, 2, 3 tails that were on it originally, and then we've got 2 more there, so that's 5, 2 more there, that's 7, 2 more there, that's 9, and then 3 more there, that's 12, all in total. So we've got 1, 2, 3, 4, 5, 6 pairs of windings inside there, and now I've got to figure out what that all means. So I'm not entirely sure of the significance of this. I've got all of the yellows off, these bits off apart from one, and on this one, looking closely, there's 2 wires going in that side and there's 1 wire going in this side. I'm going to take this off anyway, but just showing you basically what dilemma I am at. 12 ends. So now I have got to, 5 glass left on them. Now I've got to get the ohm meter out and pair these up. And after that, I believe the way this is wound, you can see in there, the way this is wound, I believe these 2 coils here are together, and then these 2 coils here are together, so there's 6 pairs basically, which will give me the 6 wires coming out, which I'm looking for. And then I can link them in each way I want, you know, put them into the... I was just going along merrily, and then I picked this wire up, and, well, it was down here somewhere. I just picked it up, it went, oh, that's a bit loose, and yeah. So, doing that is a no-go. Okay, this is the motor out of the Bridgeport, and that is the shaft end, not shaft, C pointing to and D, shaft end. Anyway, I have cleaned all of the dust out of it. There was a considerable amount of dust inside there. And we're trying to go from 3 wires to 6 hanging out. What 4 poles means is I don't care. The only thing I'm looking for is inside here, see these yellow insulation wraps? One of these will have 3 wires going into it, and all the rest will have 2. Anyway, back to the point. There's going to be 3 sets of windings basically, hence 3 wires come out, and when 6 wires come out, that gives you the opportunity to wire it star or delta. Obviously, to run it on an inverter, they're all 220 unless you want to spend megabucks. So we want to run it on an inverter, which is 220, 240 volts. And when you see 3 wires coming out, it's going to be wired in delta. So we want to be able to change it from delta to star. That's basically what I want to do here. The other 3 wires that would have come out from here have been packed inside here and soldered together to make it permanently wound in delta. So all I need to do is find the 3 wires that are inside there, because all the other ones will be pairs or 4s. Okay, but there'll be one set in there which will either be 3 or, oh, got a little finger in, it's here, or 6. I can't get it in, but it will be in multiples of 3. And since there's only 3 wires coming out, I should imagine there'll be one in there with 3 on it. But it depends. We will see when we come round to this one here. So we'll see the wires come through the casing here, wrap round here. You can see them coming round here. And the first one goes into this one here. So my next port of call is going to be cutting off this fiberglass tape, which is impregnated with varnish. At that point then, I'm not going to dig into this first wire which I just pointed at. I will observe it, see if I can observe it, but I'm looking for one of the, I think this is going to be this one here. This looks favourite. I'm looking at this one here. You've got one wire here, where my fingernail is, just there. And then just below it, right there, there's another wire. I think that's going into this one. It certainly looks like it. So this one here, this is it. I could just, I think it's going to be that easy that I'm just going to pull off these wires here. Probably cut that one, 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 probably that one and another one to give myself a little bit of leeway. Maybe not even that. Probably just start there and finish there and pull that one out. And I think that is the baby I'm looking for. So yeah, I'm just going to make sure that, yeah, it certainly looks like there's 2 going in that side. So I think we'll just peel off that one for a start and we'll see if there's just 1 going in that side. So I've picked it out a bit further, and on this blade here there is definitely 1 wire going in that side. Yeah, and then on this other side there is 2 wires. So I think I've looked out and gone straight to it. So I'm going to attempt to cut it, I think about there, to give myself about 3/4 of an inch. So I can just peel them up in the air a little bit. And then this one here, I'm going to try and cut it, I think, there. I'll try and cut it there, I think. And there. And then just leave that little bit of section of wire inside there, collected to absolutely nothing. And hope, and I'm hopeless, that that is the right wires to cut. Because if it is, I'll have this done. Oh. Right, I'm sorry for the shakiness, I've just zoomed in so you'll notice every single little shake. So, what I've done is, and ignore the background because that's what it's like, that's what I have to put it with at the moment. 2 wires are in this side, and 1 wire in this side. I've just took that off there, but you don't want to rip it off because it's got varnish inside it. So what I'm doing is I'm just gently breaking all the varnish out and then giving it a quick tug, see if it's going to come. Nope. Give it some more squeezing. I can feel the hard bit there. Just give the hard bit a good squeeze and then give it a good tug and see if it comes off. And there's no point brushing, you've got to get all the varnish off of the 2 bits of fiberglass insulation, and eventually it will come off. Give it some more tugs, give it some more squashing and squeezing. I think that's got it. Right, it's still attached to the other bit, I don't know how, but I might cut this one off because this one's been a pain. So I might just go up here. See what the problem is. It's attached down the bottom here. It's attached just was just all the varnish, just be careful. Right, now I've got 2 wires in that one, 2 wires in that one, and there should be 2 wires in that one. Yep, so now I've got to solder them and work out which one is connected to which one. Undoubtedly they will be. So let's zoom back out and get the multimeter. Now we have the multimeter and it's set up for diode testing. So when you've got a diode tester, it's always handy to have the beep. And since we've got the beep, we might as well use it. So right now, hopefully, none of these will be connected. No, and they would have been before. So that's good. That was amazing, the first one we touched. That's not connected. And that's not connected. Sweet, this is looking good. I think I've sorted it. Right. So that one there, we'll stiff that in there. That one is, I'll try to stiff that one in there. I'll twist the ends up a little bit more and stiff that one in there. Yeah. Then we'll test the next one. Make sure that's not connected. Obviously can't connect it to that one because I've already tested it to that one, so they're all not connected. So the multimeter, this is what we are going at next. What we need to determine is where the tails meet each other, and if they are meeting each other, and if I've broken the motor or not. So first port of call, let's see if these wires are still connected, because when the 3 were soldered together inside the motor, these were connected. Test the meter, and for some reason I've got it on the wrong scale. So it looks like I've cut the right wires because these aren't linked together anymore. That's good. Now we need to determine which one of these wires is touching one of these wires. So let's go have a look. No. No. Yep, that one there. So this one first to the right is going to be going to this one here. I might as well put this one closest to it. Find a little hole to tuck it in. There we go. Now this one here should be connected to the one. That's connected to that one. It's not connected to that one. And it's not connected to that one. So that one there, let me go around closest to that one, to remind me of that. Yep. So this one must be connected to the other one. It is, and it's not connected to the other ones. It can't be, I've already tested it, but double checking doesn't harm. So success. Right, next I have 3 coloured tapes, and I suppose it would be a bad idea to get the multimeter out of the way. So just get out of the way for a second. And I've marked the cables with the different colours. So we've got green, blue and yellow. Doesn't matter what these colours denote. All they are is a reference and on the outside of the casing we've got, I think that's just about where the blue wire goes in. I don't know if you can see inside there, where my finger is, inside here. That wire wraps around and then comes out. So that's where that one starts. This one here I can't see in, there's no vents there, but that's about where that one goes in, and the other one is around about there. So we've got to sequence these wires A, B and C, and it would make sense if they had some sort of rotation. So if we take this one as A, and that one as B, and that one as C, so we want terminal 1 of A going into A, coming out of A and going into C, going into C, coming out of C, going into B, coming out of B and going into A. So we get a rotation going. Fingers crossed that's right, because that's the way I'm going to wire it. And see if it turns. So the next protocol is I'm going to solder all these wires onto these and heat shrink them on and then cable tie them down. So I'm moving on to the soldering, and I've got a jig set up, which is my electrical pliers and my flat blade screwdriver holding the wire in the appropriately good angle so it meets up with the other wire inside. Now I'm using this white speaker cable, which should be gold plated, looks it to me, and it's going to wick away the temperature of your soldering iron really quickly, and I believe they usually use gas soldering when they're doing this. So I'm using a big soldering iron, don't know what watts it is, I think it's 150 or 250 watts or something of power, and hopefully that will get soldering really fast. I'm going to fill the joint up basically. I've scraped the enamel off of the ends of the wires here, here and here to bear the copper way round, and well, I've cut this wire back a considerable amount, and fingers crossed I've got a steady enough hand to do this. I don't doubt it. Like I say, I'm just flooding the joint with solder in the hope that that's enough. To coat the inside of the joint. And that should be flooded. Certainly looks it to me. I mean, it's proper overkill the amount of solder I've used, but at the end of the day, I want it to be glued together with metal. Turn the meter back on again. Try not to lose the solder by putting it somewhere stupid, like right behind you. I can't remember which wire it was. We're just on there. That's that one there. Test the meter. Yep. And I think that should be this one. Yeah, that's a good joint. I'll put it into ohms, we'll iron that out. So that's 8.2 ohms. You can see that? Yeah, you can see that. 8.2 ohms. So clearly I'm looking for the rest of the circuits to be around about 8.2 ohms. I don't want to confuse myself. Next, anyway, heat shrink. So we'll pull the heat shrink down, and that's covering the fiberglass of the wire coming out of the windings, and it's also covering the insulation on the new wire going in. And we'll use the soldering irons heat. And this is the kind of heat shrink which has got glue in it, so it will seal it to the air. Just as good as varnishing it. Sweet, that is done. Final thing is this was yellow. This was the yellow one, so I want some yellow tape. With the yellow tape, and mark that one as yellow. So I've made the rest of the connections now, not put the heat shrink on yet. Just testing the first one, and this is green or brown, green. So green on that one. And that'll be that one done. And then the last one is blue. And this one, maybe I just forgot to say that was 8.3 ohms. And this one's 8.3 ohms, so I've got 8.2, 8.3. Maybe going to higher scale we'll get a better reading, eh? No. That's the lowest scale this goes to, the 100 ohm mark. I can't go into anything lower with this meter. Blue. Now I've got all my wires marked, I can heat shrink them all. Peel straight off. Heat shrink it, cable tie it in, and put it back together again. Right, I've come to a bit of an impasse now. Got one cable tie in. I don't think it's going to move. I'll just put a bit of varnish on it to stop it from spinning out. It's in there, but it's, yeah, that's okay. That one's fine. I'm trying to put one in here, and if I pull any tightness on it, I'm just going to damage the coils. So this one could damage the coils. So I really need the fiberglass wrap, this fiberglass wrapping material really, before I carry on. So that is what I am dilemmaing with now. And here we are, after the cable ties are attached. I just got impatient knowing that I'm going to have to wait till November for the proper insulation for this to come. That's the fiberglass stuff. So until then, we'll at least get a test out of it, make sure it runs. If it runs alright, we've got nothing catching here, which I shouldn't think so. And we'll bang it in the Bridgeport and get it turning. Maybe make some parts on it, get a vice cleaned up, get it on it, and square some stock up. Looks quite neat though. It certainly looks neater than the kitchen floor behind it anyway. this bearing, it's had grease all inside it, but it's shielded. So, one side. I might try and repack it with grease, eh? So packing bearings is a lot easier when there's not a shield on it. Basically, this is how it goes. This is the only way to do it. There's no other way of doing it. You see people just squirting it on and thinking it's done. There's only one way to pack a bearing, and that is to pack it. And this one's going to take a while because it's got a shield on it. You've got to get past the shield. So what you do is you wipe it into the bearing. So I'm wiping it on the surface of the bearing, but I'm also forcing it down and trying to get it into that shield. And eventually I'll do this enough and I will see it squirting out the bottom shield. I'm just going to keep on wiping it in. And when you've got an open cage bearing, whether it be a taper roller bearing or just an open cage bearing, it takes one wipe around, but this is going to take a little bit of time just to pack fresh grease in from the top, push all the old grease out from the bottom. And this is how to do it. All bearings are exactly the same. You just put a big blodge on top and then wipe it down into it, basically. And anybody that shows you any other technique, it is wrong. I can't tell, so we'll leave it at that. All I know is it is definitely 100% harder to turn now. And not graunchy, but harder to turn because the grease is more friction than no grease. That shielded bearing refilled with grease. That's tight enough. I like to go until the bolts just start to stretch, or the threads just start to stretch. That says to me tight and not going to come undone. Motor together. I think this front bearing is knackered. I think I'm getting a noise from the front bearing. Oh. Take it to pieces again, re-grease it. So I've spent a few minutes and we've greased it up. I've just been using my hydraulic technique again. Scrape all the grease together, put it into the same position, put it down there like that, and then just try and force it in. And now that bearing is stiff because it's full of grease. As you can see, it's a shielded bearing. So your old squirt a bit of grease onto the cover, like I see a lot of people doing, just doesn't work. I managed to get it off without taking the back cover off, as you can probably tell, which makes lining these bolts up 20 times easier. Whether I'm going to get it back on again without the back face falling off. No. Right, let's see. Got some springs on that as well. I was like, oh god, the whole lot's come out of it. But not to worry, let's see if we can get it back in again. Without any bother. That seemed to be pretty delicious. .32 or something like that. Tight. Does it make a noise now? No. It is smooth, like butter. No clicking noises. Okay, what's left to do is wire it up and see if it works. So this is not a video about wiring up inverters, this is about wiring up motors. I'm going to plug the inverter in now, because we've got to do some setting up. Funny thing about this inverter is it hasn't got an earth. Here the earth port's missing, so definitely want the motor to be earthed. Just go to touch it and it shorts out, it's going to break by the breaker. I'm touching the motor now and it's not electrocuting me. It's a good way to test it, obviously, you know, just touch it, see what happens, give it a quick, if it starts burning and stuff. And then if it doesn't, then just hold it a bit longer and then really give it some. That's the best way of testing it. Anyhow, we've got some paperwork which is going to get absolutely filthy unless I wash my hands a little bit. Right, for the time being, that is clean enough. Now I can hold paper. Dry my hands off. So settings, they come in spreadsheets like that. I figured out parameter 1 maximum voltage. So I'm going to programming. fairly slow speed, so it shouldn't be too bad. 91 jog braking time, 0.1 of a second. Cool. Out of programming. Bring the hertz down to a, let's go for a jog. So I'm going to hold the motor. Could be a bad thing, or we'll go for a jog. And it started. Oh man, let's put it to reverse. Jog. So that's counterclockwise. Put it into forwards. And that's clockwise. Okay, and then we're going to run it. This could make the motor run. She runs. And she continues to run afterwards. Let's bring the thing down to see if she'll start it. Let's see if she'll start at 7. Yeah. That's full running speed normal, that's 50 hertz. So she's running. And that front bearing has got a problem, I think. So let's take you in for a closer look. So, oh yeah, it doesn't sound good, does it? So this hasn't got an earth. So what I've done is I've brought the earth down, and with a pair of mole grips I've clamped it to the earth of this 3-phase wire, which is coming round into the back here. Now in this junction box, what we've got is obviously we've got the 3 wires which I put in, the yellow, the blue and the green, and then we've got the 3 wires which were originally in there, the green, the yellow and the blue. If you remember, I marked on the motor, so we've got green at the bottom, yellow there and then blue. So I wanted to bring the green output into the yellow input, the yellow output into the blue input, and the blue output into the green input. So I think you'll see we've done that. We've got the green here, so the top one is going into the yellow, and then we've got the yellow is going into the blue, and then we've got the blue is going into the green. And I think that's what I said. I hope it was anyway, because I wasn't really concentrating, I was just following the wires on there. So if you looked at a standard motor, you'd see the 6 terminals, and you'd see 3 wires on one side and 3 wires on the other side, and that's how they're arranged. And then all I've done is I've just patched 3 wires in from a power source. That could be your wall socket or the inverter, and that's gone straight into that terminal, it's onto 3. Now if this was wired back into star, instead of having just the straight crossbars going across there, which this is just solid, what you'd have to do is join the 3 white ones together, and then just, that'd be fine, just take them out, join them together and leave the other side as it was, and then you can run high voltage. Let's bring up a bit higher then, shall we? Well, she likes 60 hertz, 65.7. She's purring there. There's plenty of air being drawn through it. And that bearing doesn't sound very nice, does it? I think that's that front bearing spinning on the cage. I think the cage is spinning. But yeah, that was, oh, and also I've bolted the air onto the casing. So there we go. A little bit of time and patience, and we've got a motor running. Just stop it. So I'm pressing the stop button in a second. And if that was in braking stop, the old motor would have gone whoo, and span, but since it's not, it didn't. I've got it on soft start, I've got it on a soft start, which, hey, beauty, that motor is hot. Yeah, I'm not sure if those wires are right, because that motor is red hot. So I might try some different configurations, because that is toasted. That shouldn't be that hot. Yeah, we'll try some. Yeah, that's toasted. That probably means I've got a wire the wrong way around. But I will fiddle with that. Yeah, I don't think it's supposed to be that hot. I don't think so. I know it's an induction motor and all that, but that is bloody hot. Very bloody hot. So I've been messing about with the wiring, swapping all the wires about, and realised it's just a waste of time swapping all the wires about. I'm not making much difference at all. So I forgot about that. I've got the amp meter out. I've got a temperature gauge inside it at 23.2 degrees centigrade or 73.7 degrees Fahrenheit. I've got the inverter set to approximately 50 Hertz. This inverter is, let's try and focus in on that, a 3 kilovolt amp, 2.2 kilowatt, 3 horsepower motor, VFD, sorry. So this is too powerful for this, and what I was expecting was that the motor would draw what it needs and the VFD would just give what the motor's demanding. But what it seems is this is pulling a sinusoidal wave, and I think it's just pulling what it can, the maximum all the time. So it's trying to pull its maximum amount, and that looks like it's about 7 amps. This motor is rated for 3 amps, 220 volts, and £2 is it? 2 amps at 440 volts. I also have a digital thermometer, an infrared thermometer. Fahrenheit. So what I'm going to do is I'm going to turn on the inverter now, and we're going to look at the amp clamp, which is set up in 40 amp scale and it's in AC. We'll just stick it on for a run now, and we'll see the instantaneous amp draw. So it goes for 11 amps for a start, and the temperature starts rising. The casing, 22, 23, 24, 25, and now it's pulling 11 amps. I haven't seen it pull 11 amps yet. I'm a bit disappointed it's drawing 11 amps, but it is. And that drops down to about 6 when everything gets hot. So I'm a bit disappointed. Turn it back off again. So instead of letting it get hot, which it's definitely going to get hot, it's like a sandwich toaster inside there, because these wires are not big enough to carry the amperage. Unlike on my lathe, let me show you my lathe. So on my lathe here I've got another one, and this one's a 3 kilowatt inverter. Well, that's running a 2.2 kilowatt motor, and the motor runs cool, very cool indeed, and it's got plenty of power. Now I've put the torque compensation in on this one. It's set up beautifully. I can drill big holes. The lathe runs beautifully. Not a problem. Now I ordered this inverter before I'd stripped this motor out. I was expecting this motor to be 1.5 horsepower. Maybe 2. I was just expecting it to be a 1.5 horsepower. It ends up it's only a 1 horsepower motor. Now, when I run it for a long period of time, well, long enough, I got this up to 87 degrees centigrade, and that's pretty much the core temperature. It's measuring the core temperature inside there, and I don't want to take it above that. It's a Class E rated insulation, and it can take 120 degrees centigrade core temperature maximum, and it has a reasonable life expectancy of 120 degrees centigrade. So I don't want to run it at 120, I want to run it well below that. I'd rather get it down to about 50 or 60 core temperature and an external touch of about 40 degrees under full load. So 10 amps coming out of that, and this is 3.5 amps at 1 horsepower. So 3 times 3 is 9 plus 1.5. This is putting out its rated power. Trying to put out its rated power. Now, that's okay, that's good, but it's too powerful. I was expecting it to drop down, and it does drop down, but it only drops down because the resistance builds up inside this, and that will be building the resistance up inside this, and that will be damaging this. So I don't want to damage this, and I don't want to damage this. And I ordered this thinking this was a bigger motor. So what I've done ahead and done is I've ordered a 1.5 kilowatt, which is half the power of this. They're relatively inexpensive, and I'm sure I'll get use out of this for some other project. And that should reduce the amount of energy going into that by half. It will keep the temperature down. Now that's still going to be overclocking this motor to 1.5 horsepower, probably 2 horsepower. But fingers crossed that will sort out the temperature problems that I'm experiencing. I've had a long and hard think about it, and I've been swapping these wires around, swap that back to its original configuration, do a few more final tests just to make sure that's drawing less amps, and if I'm correct and it balances out better, I'll leave all the wiring set up the same, get the new inverter, and we should be good. If not, then I will get the next size down inverter. These are approximately about £50 each, so it's still cheaper having 3 of these, if it ends up being 3, even 4 of these to get the right one, especially because I can use these on other projects and I haven't had to have 3-phase wiring brought into the garage. So all is good. I'm very happy that I can now reinstall this into the Bridgeport milling machine. That's what's happening. I should probably update how this has gone, but that was successful, very, very successful. Go ahead and just do that. Forget about a lot of the ins and outs that I've gone through, and just basically split your motor open, find the connection inside the motor which has the 3 wires tied together. All the rest will have 2 wires tied together. Concentrate on the one with the 3 wires in it, separate them out, put new pigtails onto them, bring them out of the motor, and then do your crossover, which
which will be diagonal, diagonal, and then back to the start again. All you need to concentrate on, and you'll do it.